Hello?
Yeah.
Oh,
Just
I couldn't hear anything.
no, I haven't
Okay.
started anything.
Okay, okay, fine.
So this is packing. Hopefully. Okay, I will. Okay, so this is lecture 19. Okay, so recall. I'm going to copy paste. So maybe I'll just do a recap so that it's clear. So recall. So first we did typicality of just a single unconditional quantum typicality. Okay, then we did conditional, and I will indicate one important point now. Conditional quantum typicality. I will just state the two, classical and the quantum, and tell you the distinction, right? In classical, so what did we do? We started with a distribution pxy, and so this gives us two marginals px and py, and so given an xn, we say so given an xn, we say yn is in the conditional typical set of xy given xn if xn comma yn belongs to t delta n pxy. This was our definition, right? And we said that if xn belongs to t delta n px, so just think about it as the marginal px and look at xn. If this is true, and you end up pulling a y, you end up pulling this y according to this distribution. So what I mean is that the ith letter is pulled according to this distribution on y. You will get a bunch of y1 through yn, and that y1 through yn. So the probability that yn belongs to t 2 delta n pxy given xn, this probability is large. Right? This probability is very large. This is what unconditional typicality says. There is one another point that you did prove in the homework, which you might have taken in some sense for granted, is the following, right? See, there is, so this pxy gives you two marginals, px and py, right? And with respect to py itself, just with respect to py, there is a unconditional typical set py, right? And you also showed so you also showed that observe that if so you proved all this, but I'll just indicate. So if xn yn belongs to t2 delta n pxy, then xn belongs to t2 delta n px. This you showed in one of the earlier parts of the homework, and this is true. And since we have defined, we say, the conditional typical set yn, so recall, the conditional typical set is essentially all those yn such that xn yn belongs to T2 delta n pxy, right? This is the conditional typical set, which means that if I ask what is the probability that we know this 2 delta n pxy given xn is is very high, we know this, but since if yn belongs to 2 delta n pxy, that means xn comma yn belongs to T2 delta n, which means that the probability that yn belongs to the unconditional set is also very high. So this is also 1 minus epsilon. Do you agree with this? So in other words, what I'm saying is, see, there is this yn space. In that, so you have chosen a distribution pxy. Now, this gives you marginals px and py, right? So there is a t delta n py, or let's say 2 delta n py, okay? And there is a t 2 delta n pxy given xn. And this set is sitting inside. So this set, so I'm going to denote this in blue color, blue. This is sitting inside this. Is this clear to both of you?
Sorry, just can you just scroll up?
Yes, sir.
Yeah.
Notation Tn 2 delta given xn. Okay, you are using this notation. Okay. Right. I think yesterday we had the xn in the subscript or something, but that's fine. Okay, that's fine. Yeah, I got it.
This is clear, right? So the fact that you prove that, remember, there is this the toughest the toughest question in the typicality homework was this: py given x, n of yn given xn, t2 delta n pxy given xn, this yn, this thing is greater than equal to 1 minus exp something minus n times something. This was the hardest question. But since if yn belongs to 2 delta n pxy given xn, that means that xn yn belongs to t2 delta n pxy, and this implies that yn belongs to t2 delta n py. This is also true, t2 delta n. Now I just include py here, just the marginal set. This yn given xn, this is also true, right? Clear to both of you?
So this is true, assuming that xn is also in the typical set.
Yes, correct. That is true, right? So what are we saying? See, I told you that py given x is kind of analogous to rho x, right? What is py? Py of y is essentially this: px of x, py given x of y given x. So it is the average of the py given x distributions average with the distribution px. This is what is py given x. Sorry. This is what is py, right? Now, similarly, I can talk of a distribution px. I can sum over px of x rho x, and I will get a distribution rho. I'll get a density operator rho, right? So in some sense, what all of this is saying, if you think of what all of this is saying, right? What is this saying is that if I choose an xn and I consider rho xn, then I can find a conditional typical projector of rho xn that overlaps very highly with rho xn, right? Rho trace of this is very high. And we know that the trace of pi rho xn, that is the dimension of that space, is 2 power n times. I mean, this I didn't prove, but I kind of indicated this, you should expect this. Sorry, you should expect this, and I kind of indicated the proof will come essentially very similar to the classical probability, right? But so all of these statements, right? All of these statements are analogous to this statement, and the fact that this size is at most 2 power n h of y given x, right? That is what these statements are. But we also know this statement, which means, so what does it mean? Now I am looking at the conditional typical, the unconditional typical set of py. What is the analog of this statement in the quantum? So what should I do? So this set, so I'm looking at the unconditional typical set of py. So what it is saying is I will fall in that typical, unconditional typical set. The analogous statement of that would be, I should look at the projector, the typical projector corresponding to rho. And what this is in some sense saying, is that trace rho xn, when xn is t delta n px, rho xn pi of rho, not rho xn, right? Here it is pi rho xn, that is the unconditional typical projector. Sorry, conditional typical projector. Here is the unconditional typical projector. This also may be high, right? Do you understand this statement? It's very important for you to understand this guess statement before we go ahead.
Sir, the conditional projector is like it projects onto a subspace larger than the conditional projector. So we can capture it. So the rho xn falling in that subspace is also with high probability.
Wait. What are you saying? So wait. You understood? I mean, Srinidhi, if I didn't point out understand, just tell me. No problem. Okay. So you understand till here, right? So
Sir, you explained with a diagram saying like the conditional one. Here like the small set like p x y given x is small, and it is like covered by the unconditional one. So like I can think of the unconditional projector as the set that projects to the T2 delta n py, and the conditional one projecting onto the smaller set, right?
Yeah, good point. But Srinidhi, but keep in mind that is true if the conditional typical projector, in some sense, that subspace is encapsulated in the subspace corresponding to the unconditional projector, correct? In other words, so I'll say this again. That is true if the conditional typical projector, the subspace on which the conditional typical projector projects, is subsumed within the subspace on which the unconditional typical set projects, correct?
Yeah.
Okay. But the problem is that is not guaranteed. I'll tell you why. See, observe. Okay, so good point. See, observe. You have rho x. So the statement only gives you this, right? The statement gives you that rho x's have some spectral decomposition, right? Y given x.
Yeah.
E y given x. Y given x, right? Now, when you calculate rho, what are you going to do with rho? You are going to do this, right? You're going to compute px of x, rho x, right? This is what you get. So what do? You essentially are doing x, y. Sorry, this summation is over y. This summation is over x. So you will do something like this: px of x, py. Sorry, this is q. I should have written q. And the reason why I write q will become clear now. This is.
So sorry, just one question. So
yeah.
That should be your sum over x ends, right? Rho is equal to summation over, can you just go up? I forgot. Rho is defined to be summation over all the row sub xn's where xn is in the typical set.
Where?
Oh,
Wait,
here.
wait.
Oh, so you're just, okay, it is not, sorry, then I misunderstood. Okay, you're summing over all the x's, not over x's. Okay, fine.
See, this is the average of these distributions, right?
Yes. Mhm.
Average with respect to this distribution Px.
Oh, you're doing the same thing. Okay, I see.
I'm doing the same thing here. So
Okay.
here the xn's was typical according to Px. So here also the xn's was typical according. So you chose your xn to be typical according to Px. Sorry, xn was typical according to Px, and you pulled a y according to Py given x, and I am claiming that the yn will also be typical with respect to the unconditional Py, that is the marginal Py, right? So we should kind of expect the same thing here. So we pick an xn according to Px. And then we are generating this rho xn, right? We know rho xn is going to be with falling overlap with this pi rho xn very highly. That is kind of analogous to the unconditional, the conditional statement. But in the yn happens to be typical even with the marginal Py that comes out. So the question is that analogous statement true? So is rho xn also going to overlap with the with the projector of the average row, right?
Okay.
Is it clear, Srinidhi?
Yes, sir.
Yeah. Okay. So now I'll tell you. So you and your thought process is correct in the sense you're saying, okay, most likely, just like in the classical case where the conditional set was subsumed within the unconditional set, similarly, you're guessing here that the conditional typical projector, the subspace in which the conditional typical projectors projects, will be subsumed in the subspace of the unconditional typical projector. Correct? That's your guess.
Yeah.
And now I'll tell you that's not necessarily true, and I'll tell you why. See, I'm just computing rho, right? When I compute rho, this is my this is my expression, right? Ey given x, y given x, ey given x, right? This is what I do. See, what am I doing? I am mixing a bunch of rank 1 operators with some distribution. Now, if I go ahead and do the spectral decomposition of rho, this could be something completely crazy. So I just go compute rho, and then I'll do the spectral decomposition. So I might get some distribution y. I mean, this is a bunch of eigenvalues, and these rank 1 operators fy, right? I have no way to relate these two guys. So now if I look at the typical projector corresponding to this spectral decomposition, I have no clue whether pi rho in some sense includes pi rho xn. You understand?
Yeah.
This is really the problem of non-commutativity. So when you are mixing rank 1 projectors, right? When you are mixing rank 1 projectors, the resultant operator, its spectral decomposition can be completely, there's no relation between the rank 1 projectors that you start out with. See, here, what happened is when I was mixing, so when I mix this px, py given x, right, I get py, right? Now I don't have any guarantee that ry of y, I have no guarantee that ry of y is equal to this. You understand? So that is why I did not use P here. And that is why I'm not going to use P here. I'm going to use R. You understand? So it's all coming from the spectral. So somebody gives you the rho axis. You just go ahead and compute the spectral decomposition. You will end up getting with some qy given x. Then what you do, you mix the row x's, you're going to get some row, then do the spectral decomposition, you're going to get something. There is no relationship between these objects, this distribution with which you mixed, and the resulting eigenvalues of the rank of the resulting average projector. And there is also no relation between these eigenvectors and these eigenvectors. You see? And hence, it is not at all clear if so what you do, so let me explain this. So I will just state, so what you took a bunch of row x's, right? You just took a bunch of row x's. Then you just took an arbitrary distribution px. You took a sequence xn that is kind of typical with respect to px. So I'm going to write this t delta n px. And what you do is you look at row xn. So what is this? This is your row x1 tensor all the way until row xn. Now, and this px, you mix these row x's with respect to this px. I'm stating this once again, just for kind of clarity, so that we don't go too fast. So you get this row. Now you consider the unconditional typical projector of row that is defined uniquely from row, and you ask the question, hey, does pi row overlap with row xn? And there is no guarantee. Okay. And this is an important thing, because essentially that is why I used qy given x, px, and ry and all that. Okay, so I just wanted to state this. This is a good, maybe a way to recollect also everything. So there is this distinction that you have to keep in mind. But it turns out, so there's something called, this is now become very common, but it is called, some people call it pinching lemma. And it's an important, it's not an important thing, but it's used everywhere. It is important, it's used everywhere, but it's not too hard once you do it. And this is something that you should also, kind of master. It turns out that this is indeed true. It turns out that this is indeed high. It's not 1 minus epsilon. It's going to be 1 minus something, but, it is going to be some function of epsilon that also goes down to 0. But this is indeed true, but it is not as straightforward as in the classical case. And we will prove this at a later point, maybe in the next class, or the prove it at so. Okay, is this clear?
Sorry, just one question. This trace of pi row xn, its classical analog would be what? Like pi row's classical analog is p of y, correct?
Its classical analog will be exactly this. Yn belong to T2 delta n of py. So projection is like looking into a subset. So this is the projection on the unconditional typical subspace of rho. And this is the typical set corresponding to the unconditional distribution, that is the marginal py. Rho is like the marginal, right? You do px of x rho x.
Yeah, correct. Rho is like the marginal. Correct.
Yeah. So if you pick rho xn, if your quantum state is rho xn, then it overlaps with pi rho. The equivalent statement of that is, suppose I pick according to p y given x, yi given xi, right? Product I equal to 1 through n. The probability that not only I fall in the conditional typical set of y given x, but also the unconditional typical set of y itself is very large. So this is the equivalent statement. And if you observe, this is in some sense straightforward in the classical case, simply because xn, yn belong to T2 delta n implies this just comes essentially from counting. And so this is true. And hence,
I see. So in the classical case, we have this inequality when yn is taken from the conditional typical set. So we also have it for the unconditional.
Yeah, we also have it for the unconditional.
Because of what he wrote on the right side. Okay.
Exactly.
And xn is known to be in the unconditional typical set.
Yes,
correct?
exactly.
Okay.
Xn is known to be in the T delta n px.
Okay, so this left hand side thing in the box just follows from that. Okay.
Yeah.
Okay.
But here it doesn't follow because you can't make that statement. You can't say that. You can't even say that the typical projector of the conditional typical projector of rho xn is subsumed within the conditional typical the unconditional typical projector of y. That is not at all guaranteed. It's actually
Okay.
not true. It's actually not true. They do actually they are actually distinct subspaces, but you can somehow try and argue that they are close, and that's how you kind of show it. Okay, is this clear?
Sir,
Yeah.
Yeah, Srinidhi.
Sir, the pyro would be like represented as like the tensor product of sorry, tensor, not the, it would be the this one, the endpoint projectors of this FY.
It would be this.
Yeah. Yeah. Yes. Yeah.
And this would be ry.
Ah.
You understand?
So RY is my new distribution.
Yeah, ry is no way related to this pxqy given x.
Yeah. If
And
it was
even the
classical,
F-
like I would have got the marginal one.
Correct. ry is coming out of the spectral decomposition of rho, for which you have no control over.
Yeah.
So this is really the the non-triviality with the quantum. But anyway, let's go ahead. So I think this is a good review because it kind of indicates both the parts and also indicates the quantum thing. Okay, so recall yesterday. So I will copy paste so I think these two definitions are clear, right, to everybody. That is, what is a code book? Essentially a selection of code words. So recall the kind of the terminology. This is the code book. Each thing is a code word, and you have a measurement corresponding to that code book. You're trying to recall, you have a CQ channel and you're trying to communicate messages, and the states are not orthogonal, and you need to do all this. And when I have a code, so that means I have a selection and I have a corresponding POVM. I have an average probability of error. So this is just the probability. This is just the use this. This is just the probability that this guy. I mean, Alice chooses message M, but then Bob has got an outcome corresponding to something not M, and then I average over all M, and that I will denote it as xi of e comma lambda. E is just the E. I'm just using as a kind of a short form for this code book. That's all really, because E is just the map. So I'm just using it as a shorthand for the code book. So I don't want to write the entire code here inside xi. So I'll just say xi of e comma lambda. This is it. Is this clear to both of you? Just put a thumbs up if it is. Okay. Okay. Then I have this. What I mean, so read this. I'll give you a couple of seconds, read it, and then I will. So I say a rate is achievable if no matter what is my desired probability of error. So let me read it my way. So a rate I say is achievable if no matter what probability of error I desire, I should find a code book with a large enough n, that is so one more just a notation. So when we say when we build a code, our code will be like so there will be 1, 2, these are the possible messages, right? Message possibilities for the message. And what I do is I'll do this, right? X1 of 1 all the way until xn of 1, x1 of 2 all the way until xn of 2, and I do x1 of 2 power nr all the way until xn of 2 power nr. And usually this n, right, this n is called the block length of the code. So I'll just introduce some terminology. Block length of code. So R is the rate of code. Yeah, these are called the code words, and the entire collection is called the code book. Okay. So what this definition is saying is, no matter what is, so I say a rate R is achievable if no matter what is the error probability I desire, I should find a code of a sufficiently large block length. So I'm willing to wait. That's what we started to do, right? I'm willing to wait for long enough. There should, but there should be a code with rate R, block length N, an encoder map E that is a bunch of code words of size, code words of size N and rate R, and a corresponding POVM, such that the error probability of that code has to be less than epsilon. And I should be finding this for all n greater than something. So, if you give me 10 power minus 27, okay, I will go to a size of length, a block length of size, say 1 million. And for every block length 1 million, 1 million, 1 million 2, 1 million 3, I should find codes so that the error probability is less than epsilon and the rate is R. You can say, okay, why do I want if I find it for 1 million, that's enough. Why do I want it for 1 million 1, 1 million 2, 1 million 3 block lengths and all that? That's okay for technicality. It turns out that once you find it for 1, you can find it for anything larger. So, but don't worry about it. So this is the definition. And if you don't understand definition, ask me. Just put a thumbs up if it's clear to both of you. Okay, so what are we doing? So the question is, what is the maximum rate at which I can transmit? That's what is called the capacity of the CQ code. Okay, so the capacity of the CQ code, so I'll define it like this: capacity of the CQ channel. The CQ channel is completely characterized through this collection of density operators, right? So the capacity of this is the soup, the maximum over R, such that R is achievable. That's all. Okay, and it turns out we will use the packing lemma in order to kind of give a value to this C. That's really what is going on. The idea is also why packing. So I'm going to just kind of maybe, okay, I should not go into the previous notes. I'll continue in this notes. So why do we call packing? I'll tell you in the classical case, why do we call packing? Okay, and it turns out the same thing applies even in the quantum case. See, the idea is very simple. So you take rho xn, right? It lives in a subspace of dimension something, right? Okay, maybe I'll do it in the classical. It's slightly easier. I'll quickly motivate this, and then I'll go to the. So you have x and you have y, right? And there is this channel wy given x. So what did we observe? So it also relates to what we did now. Suppose I choose an xn and I kind of input on this channel. I will get a random yn, right? What is this yn? This y1, nature would have pulled it according to the distribution py given x of something given x1. It would have pulled according to this distribution. And yn, it would pull according to this distribution. It would just sample according to this distribution. That's really what's happening. And what we observe is that we observe the following. With high probability, the entire sequence yn will be in a ball of size. So the yn is marginally, it is typical according to the marginal distribution py. So it will definitely lie within 2 delta n py. This is for sure. Also, with this is all, the other thing that is also for sure is that if you choose this xn, then you will fall within a set of size. So this is your 2 T delta N Pxy given Xn. So we showed that it falls within the blue set, and the blue set for the blue ball, and the blue ball falls within the red ball. Now with high probability. Okay. So what if I can find, the whole idea is the following, right? Suppose I can find an X tilde N, a green X tilde N. Okay. That will fall, say, whose ball will be disjoint with the blue set, right? Suppose I can somehow show that T2 delta N Pxy given X tilde N is in some sense disjoint from blue, then I can use these two as code words, right? And I can use these conditional typical sets as my decoding sets, right? So I can say if yn falls within the blue set, you declare it was the xn code word that was sent and the message corresponding to this. If it falls within the green set, you say it was the code word x tilde n that was sent, and it was a message corresponding to that. Similarly, if I can find, let's say, a pink x hat n, whose ball is again disjoint from the green and the blue, then I can use that also as a code word, right? So the question is, how many such conditional typical sets can I pack within the unconditional typical set? That is why the maximum number of such packing gives me should give me the maximum rate at which I can communicate. Is this clear?
Sir, so like we are packing 2 to the power nr balls inside the marginal distribution. So then we can say R is achievable.
Yeah, but I want to know what is that R. And see, I could see, suppose okay, so let me tell you. I will use this picture and explain. See, suppose my yn set is like this and my red set is like this, and suppose one particular choice, right, does something like this. Suppose, I'm going to, these are all multiple disjoint multiple conditional typical sets. Suppose it turns out like this is the packing, but I'm not able to put anything here, suppose. Okay, then the rate will be, I have essentially packed 1 2 3 4 5 6 7 8 9 balls, correct? But suppose a different packing enables me to pack, say, more number of balls, then that's a better packing, right? That gives me a higher rate.
Does the size of the ball also matter or something?
Remember, what is the size of the ball? The size of the ball is not just the size, even the location of the ball matters. It is not just the size, it is the location. So if you take a particular xn, it corresponds to a particular 2 delta n pxy given x tilde n, given xn, right? I take x tilde n, this corresponds to this. It's not clear if these two guys are disjoint, right? And it's not clear where these two guys are, correct?
Yeah.
So you have to somehow, in some sense, in a blind way, choose those sequences that permits you to pack the maximum number, both in terms of, geometry, size, whatever and whatnot, correct?
Yeah.
That's exactly why, this whole problem of, communication is referred to, is kind of seen as a problem of packing. So so that's why this is referred to as a packing lemma. In the quantum case, all that happens, these sets become subspaces. So now we are in a big ambient space and you're trying to pack orthogonal subspaces. See, disjoint subsets correspond to orthogonal subspaces. So what you're trying to do is to pack orthogonal subspaces in a big ambient space, and that's why it's referred to as the packing lemma. Is it okay?
Yes, sir.
Okay, so I will now go into the packing lemma. So and you can guess, actually, from here you can kind of guess what is the capacity, because see, this is the size. What is the size of this?
2 raised to h of y times
2
n.
raised to h of y, right? What is the size of these blue, red, and pink balls? It's the conditional typical ball. So it's going to be 2 power n h of y given x, correct? So how many can you pack? If the big space is of size this, and each one is of size this, how many can you pack? You can pack 2 power n h of y divided by 2 power n h of y given x. So this is 2 power n h of y minus h of y given x. So this should be equal to 2 power n r, and r is going to be h of y minus h of y given x. So similarly, in the quantum setting, you can conjecture. Remember yesterday I told you what is h of y? H of y is like this, right? S of px rho x, because it's the average. The py is the average of the py given x's with the averaging distribution px, and this guy is essentially px of x s of rho x. Are you do you both agree that these terms are corresponding?
Yes, sir.
So you can expect the rate of the classical quantum channel to be this. And if you go back to your quantum entropy channel, I actually showed that this is a non-negative quantity. We showed that the first term is always greater than equal to the second term. So this is indeed going to be your capacity. So we will actually kind of prove this, but the main tool in proving this, I mean, the book does it this way. I really started doing it this way when I learned it, but then later I really don't explicitly prove the packing lemma, but just to help you kind of be to be able to also read the book, I will do it exactly like the book does. So we'll now kind of prove the packing lemma. So packing lemma is a lemma saying how many orthogonal subspaces can you pack in a big in a big ambient space. Just like in the classical, the question is how many conditional typical sets can you pack in the big unconditional typical set. Similarly, how many conditional typical projectors you can orthogonal. See, they keep this in mind. You choose any xn, rho xn will overlap with pi rho xn. Okay, that's no big deal. This is size. Has dimension 2 power n h of this has this dimension. Sorry. This has this dimension, but the key point is you want to choose xn of 1, xn of 2, all the way until xn of 2 power nr, such that the pi rho xn of m, these are all having orthogonal support. The reason for orthogonal support is that you want to decode it. Your measurement has to give the right message. So the key point is has to be asymptotically orthonormal. It has to be asymptotically having orthogonal supports. That is the key point. Just like in the classical case, you want to choose those subsets that are disjoint. Here, you want to find subspaces that are asymptotically orthogonal. Is this clear?
Yes.
Okay, so now I will state the packing lemma. Okay. So the packing lemma says the following. See, what do we do? So I will motivate, I'll motivate the actual statement of the packing lemma. The statement is slightly, he's written it in a slightly different way. I use slightly different terminology to make it more clear. See, you had these collections of rho xn's, and your goal was to choose a subset xn of 1 to xn of 2 power nr and a corresponding POVM with these operators, such that you such that the following holds, right? 1 minus trace of lambda m rho xn of m. This when I average over 2 power nr, I do the sum over m equal to 1 to 2 power nr. This is small. This is what really we are looking at, right? So, so what I'll do instead of, I want to state the packing lemma in a slightly general form. So what I'll do, this xn set, I will call it the set Z. So I have a bunch of density operators on Z. Okay, so these are density operators. So these were belonging to D of Hn, H tensor n. I will just say just to keep you to make the right connection, I will call these to be density operators on some H with, I'll write an extra line so that you should kind of think of this as H tensor n when you apply it to the previous problem. So I have a bunch of these operators, and I want to do a sub collection. So I will call that sub collection, keeping in mind the word code book, I'll call that sub collection as C. So C is a bunch of C is a sub collection of Z. Okay, and so and the size of C is what I'm interested in. I want the size to be as large as possible. Let's call the size of this to be M. Okay, so this is kind of analogous to 2 power nr. Okay, and what do I want? I want, so if I take, so what is C? C is like C1, C2, all the way until C capital M. Okay, and what do I want? I want to also come up with a pi, not a projector. So instead of calling it pi, I'll call it gamma. So I want to find gamma 1, gamma 2. These are positive semi-definite operators that sum to identity. And I want the following, right? I want 1 minus trace of gamma m. Okay, there is a 2 gammas. I don't want 2 gammas. So I'll call this theta, okay? Theta 1, theta 2, all the way theta m. So these are your, these are the elements of your POVM. So if I do theta m, gamma cm, right? Cm is cm each. So think of Z to be 1 all the way until cardinality of x to the power n, right? This, so many choices you had, and you would end up pulling, so C would be some set, right? It could be 3, 7, 12, like something. This would be of size 2 power nr, right? And so if I look at this 1 by 2 power nr, and I sum, and I sum these, m equal to 1 to 2 power nr, this has to be less than epsilon. This is my goal, correct? So I will go ahead and state the packing lemma using these terminology. So my packing lemma will have the Z, will have the gamma Z, and all of that, and then we'll identify the C and all that. So look at the packing lemma, and then once you understand it, we'll go ahead and prove it. Packing lemma. Suppose Oh, I said okay, that's correct. Okay, so suppose I have a collection of density operators and a distribution PM and a PMF on Z, for which there exists some projectors and a projector pi such that four conditions hold. I'll explain these four conditions physically. So trace pi Z rose, pi Z gamma Z is greater than equal to 1 minus epsilon. 2. Trace pi gamma Z is greater than equal to 1 minus epsilon. 3. Trace pi Z is within the dimension of the subspace on which pi Z projects is at most D for all Z. So everything is for all Z. 4. Pi Pz of 0 gamma Z. So let me write it this way. Pi gamma pi is less than equal to 1 by d pi oh, I should do something. Okay. I will let you read this and then I'll explain and then, connect it to the previous thing and then we'll prove it. I'll give you a few seconds to kind of read this whole thing and I will then kind of explain it and then we'll start proving. Maybe what I should do is actually just give me 1 second. Let me actually do this. Let me actually so let me open another window so that you can see both the yeah. Okay. I'll tell you why I'm doing this. I'll explain how you should kind of keep these guys in mind. Okay, let me okay, so on the right, let's do one thing. Give me 1 second. Copy page. I'm trying to make another copy of the same page. Let's see. Okay. Okay, great. Okay. So, okay. So here the gamma z's, right, are exactly like, so one. Okay. The gamma z's, right, this is exactly like rho xn's. Okay, is a collection of density operators. This pz is just like pxn, pxn. So that's your distribution on x cross all the way. Okay, is a PMF on xn. So I'm just writing in red what it is for the previous case, for which there exist these projectors. Okay, so maybe okay, I'll be slightly careful here. Let us say instead of this, let's say this z. Okay, so let's do this. Xn belongs to T delta n px. So it is the set of all those density operators where the xn's are typical with respect to px. So you're only taking those density operators, rho xn, where the xn is typical according to px. So take that collection. There is a PMF pxn on xn. There is no change in that. For which there exist these projectors pi z, such that the overlap between the projector pi z and gamma z is very large. So what is pi z? Pi z corresponds to your pi rho xn. Okay. So suppose you have a bunch of density operators and there is a distribution on that ambient set, and there is a collection of projectors pi z that overlaps with these gamma z. So the pi z is, conditional typical projectors. I also told you this is not guaranteed, but okay. So before I go there, then you define your pi to be the unconditional typical projector of rho. What is rho? Rho is summation px of x rho x. I told you, I didn't prove this, but I told you that it turns out the unconditional typical projector also overlaps with these rho xn's. So suppose you have that, which turns out to be true, which I have not proved, and I have a bound on the dimension of these conditional typical projectors. I indeed know D. What is D? D is 2 power n px of x s of rho x, right? And it turns out pi sigma pi, that is, we know this. I'm going to write it at the bottom. Pi, if I look at this, px of x rho x pi, I know this is less than equal to 1 by 2 power n, s of rho pi. I know this, right? This is coming from your operator dominance. Suppose there is, and what is D? D happens to be 2 power n s of rho, right? If all this holds, then there is indeed a subcollection of these indices. So there is a subcollection of this T delta n px set of all of that. There is a subcollection of size capital M, and there is a POVM for which the probability, average probability of error is at most 2 times epsilon plus 2 times 2 root epsilon. This is not a big quantity because we can push these epsilons down. So this is not a big quantity. And the last term is 4 into m d by d. So if your m is less than is less than capital D by D, then you can push this guy down to 0. So as long as your m is less than capital D by D, then you can push this down to 0. And from here, we know this capital D is 2 power n s of rho. Small d is 2 power n px of s x s of rho x. So if we choose m to be, let's say, 2 power 2 power n s of rho minus px of x s of rho x minus some small, let's say, delta, then m d by capital D will be equal to 2 power minus n delta. So which means I can push this term also down to 0. So that is what this packing lemma is kind of telling you. I know it might be confusing, but tell me where your confusion is. So I do expect that the packing lemma might seem a little bit very weird. If it does, just put a thumbs down and I understand.
So in the third point,
Yeah.
so that is the conditional typical set as per Z, correct?
As per rho xn, correct.
Okay, size of the, okay, so pi Z is supposed to be the conditional typical set of Z. Okay.
Yeah, it is the dimension of the subspace of the conditional typical projector.
Okay.
So this packing lemma is telling you conditions under which you can find a subcollection and the size of that subcollection. That's what it is doing. So you're saying, okay, suppose, you know, you choose these, you happen to have these gamma z's, for which you can find conditional typical projectors that overlap a lot. And you have a bound on the conditional typical, the dimension of the conditional typical subset, subspace. And furthermore, if these gamma z's are also encapsulated in a bigger subspace corresponding to a projector pi, so not only can you bound the dimension of each fellow, but you can also tell that they are within a bigger ambient space, and that bigger ambient space corresponds to the subspace of subspace on which pi projects. And furthermore, you can, this fourth condition may seem a little bit weird at this point, but it will become clear, if you read this a few times. These conditional typical subspaces are kind of evenly distributed in that ambient space. That's what the point 4 is saying. Then you can end up finding a subcollection of size capital M, whose probability of error falls as at the end of the day 4 times M into little d by capital D. So little d is the dimension of the subspace on which the conditional typical projector projects, and capital D will eventually turn out to be the dimension of the ambient subspace. That's what this packing lemma says. So in some sense, it is in some sense what it is saying is that, okay, you almost have all the ingredients now, because you have proved you have identified the pi z's. You've identified a pi, you've identified your PZ, you've done all that, and the packing lemma says, okay, I am going to give you a subcollection, and I'm also going to give you a POVM, theta 1 to theta m, so that what you want is satisfied. That's really, in some sense, the packing lemma is kind of telling you, okay, you can solve this problem now. Does it make sense?
So this,
yeah. Srinidhi, go ahead.
Sir, in the fourth one, you said something like operator dominance. You wrote that it is less than or equal to 1 by 2 power ns rho pi.
Yeah. Recall this. Yeah, tell me. Complete your question.
Yes, sir, that I did not understand.
See, I'll tell you what is happening. Okay, so let me think the right way to explain this. See, what that condition is saying is, you ended up choosing your gamma z's, and you ended up choosing your p. You have some gamma z's in your mind, you have some pz in your mind, and you have some pi z's in your mind, and you have some pi in your mind. Okay, this packing lemma is asking you that this should hold gamma pi. This has to be less than 1 by capital D pi. Okay. What is gamma? Gamma is your gamma pz of z, gamma z. So wait, let me backtrack a little bit and explain. So maybe I'll do this. I'll remove this from now on. So let's go back here. Yeah. So okay. See what this packing. See what all do we have so far? We have this row xn's. We have designed these row xn's. We have identified some row xn's, for which we have identified pi xn's. We also observed that I can define a row as px of x rho x. And I told you that though it is not obvious, it turns out that there is a pi, right? For which trace pi xn rho xn is greater than or equal to 1 minus epsilon. Trace pi rho xn, I told you, is not obvious, but it also happens to be greater than 1 minus epsilon. We also have a bound on pi xn, right? Some quantity here, which I'm not going to write. And really what we are looking is, can I find xn of 1 all the way until row xn of 2 power n r? This is really what my final goal is, right? And the packing lemma is telling you that indeed, yes, I can find for you a collection C or xn1 all the way until xn of m in some sense, and a corresponding T1 to Tm. I can give you all this for you. I'll give you all this such that what you want is satisfied. But this is another condition that needs to hold. Okay, and you observe that in your statement it does hold, because observe the following. If I do pi pxn of xn rho xn pi, this is because this is in the xn belonging to t delta npx. You can think, okay, this is going to be very close to pi rho tensor n pi, and we know this is less than equal to 2 power minus n s of rho pi, right? So we have this inequality. So this packing lemma is saying that that is also needed for me to be able to give you these things. That's what the packing lemma is saying. I think you might have a little bit more doubt, but kind of tell me something and I'll explain.
So I have one question.
No, one second. Let's Srinidhi complete.
Yeah.
Yes, like I think I should read again. So
You have no this. See, I have kind of not explained this because that requires a slightly different viewpoint. I will try and do it in the next class. It requires a slight viewpoint why this condition is required. That actually is bearing on the proof, and I'll kind of do it in the next session. But yeah, I understand your doubt.
sir.
Yeah, Tejas, go ahead.
This pi you said is analogous to rho, right? In the previous thing.
No, pi is analogous to pi rho.
So rho is something which is on the Hilbert space H,
Correct.
and gamma is something, and pi is something on the Hilbert space H tensor n, like n copies of that.
Now let me open this window. It's better. Yeah, go ahead. Now we look at it, and then you will.
Yeah. So in this case, so you have that pi arrow row near the second line. So what is that like? How is pi corresponding with rho?
So pi is like pi rho. So,
pi sub rho. Okay.
Pi sub rho. It's the unconditional typical projector of rho. So you average the rho x's or rho xn's, you'll get a rho. It is the unconditional typical projector of rho. So this is the property I told you is true, but not straightforward to prove as in the classical case. This is the property I told you.
Okay. So that. Oh, I see. Okay. So even if rho is on the Hilbert space H, pi rho is something, is a projector on H tensor n sort of.
Yeah. I understand your doubt. See, the way you should think of it is the following. So all of these analogies are correct. The only thing that might be confusing to you is, okay, gamma is somehow p xn of xn rho xn, but the xn's are only inside the typical set. And you might be, but rho tensor n is not that, right? So that is maybe your confusion.
Rho tensor n is not inside the typicals. Yeah, correct.
No, rho tensor n is the summation over the entire xn. But here, so I understand your doubt. And I'll explain your doubt, and then we'll find a way to see. what do I have? I have gamma z belonging to z. And this I told you is kind of analogous to rho xn. Xn belong to the typical set because I need the conditional typical projector, right? So then there is a pi z, which is kind of analogous to pi rho xn. Then there is a pi. Then I told you I define my gamma to be summation pz of z rho gamma z, right? If you do this on this side, you will end up getting p xn of xn belonging to t delta n px rho xn. This is what you'll end up. Okay, but really what I in some sense need is rho tensor n. This is not equal to that, but very close to. Okay, this is not equal to, but very close to. So the pi I'm talking, and the pi I'm talking about is really pi gamma. Okay, or it's pi that I'm talking about here is the pi rho, which is pi rho tensor n. I mean, I'm not writing rho tensor n, but pi rho tensor n. So now you see everything fall into place, right? Because on the left hand side, I am asking for trace pi z gamma z to be large, which essentially is asking for trace pi rho xn rho xn to be large. Then I'm saying, okay, we didn't prove this, but this ends up to be true. Pi gamma z is also asked to be large, and this I kind of told you that if you make this one leap here, I told you that it turns out it is true, but I have not proved it. Rho xn is also large. The third one it says is, can you give me a bound on the localization, that is pi z is less than equal to d? Yes, indeed, I have something like this here. Pi rho xn is less than equal to 2 power n a p x of a s of rho a. This is true. And finally, pi gamma pi is less than equal to 1 by capital D pi. Well, this is indeed true if I look at pi rho summation. What is gamma? Gamma is rho tensor n really, but there is that small fudge that is happening. Pi rho. This is indeed less than equal to 2 power minus n s of rho pi. So this guy is in the denominator, and this is the 1 by this of the is the capital D. You understand the analogy? So there is only this fudge that is happening.
So this pi sub rho is somehow saying that you are looking into the unconditional typical set of the y's, which you said in the previous.
Correct. The ambient space. Yes. The ambient space in which it lives. Yeah, that's really what it is. Okay, what I'll do is I'll end here, and then I will do the proof, and then you will see some elements. So yeah, this is slightly tricky. Well, actually, it might be slightly hard upfront, but couple of if you do the proof and I use that in the statement in the real capacity statement, then looking back it'll make sense to you. See, even for somebody who has done classical information theory, the packing lemma, the way it is stated, looks a little weird, but the connections are indeed what I have written. So we will go over it, and the good thing is, since the video is there, you can kind of go over it, and then we'll have a kind of maybe a review session or a discussion session sometime. So I will prove the packing lemma. Hopefully, if there is no objection, I'll do it today. And then I will use that, and then I have two options. Either I can go to the covering lemma or use the packing lemma, and then do the covering lemma later. But hopefully the big picture is becoming clear. So what did I do in the class? I essentially kind of recap the classical quantum typicalities and show that there is this difference, but this turns out to be true, and we will prove it. And then I kind of motivated the packing lemma. Why do we call it the packing lemma, and really what you should expect? Why are we trying to do? What are we trying to pack and stuff like that? And so now, clearly the problem required. So then I went to this definition. So we had this definition, and we're asking, what is the maximum number of things that you can pack? I should end up finding this code and this POVM. And packing lemma is telling you that, okay, you have all the ingredients. I am going to give you that POVM theta and the subcollection C. Somehow I'm going to cook it up for you. So I'm going to solve this problem for you. And all that solution is kind of encapsulated in the proof of the packing lemma, which I've just stated. Is it okay?
Yeah.
Yes, sir.
Okay, cool. So I will post this video and the thing right away, and hopefully we can have one more session. And I'm not going to teach on Tuesday, possibly may not be on Thursday also, but let's see. Actually, I wanted to know from one of you. So this is the 20th. No, I'll be teaching the 20th lecture today afternoon, evening. So the question is, how many lectures I should have had, and how much behind am I, or am I on course? I'm not completely sure. I'll do the counting today, and I'll let you know. But I'll do the 20th lecture if it's okay with if no, I get no objection. Okay.
Sir, like,
so
Mhm. If it is possible, can you do the doubt solving session today than the class? Look, like I need time to again read this stuff so that
okay. I understand. I can do it. Yeah, I think I will be. So Tejas is, let's say, is 9:30 is little late for you, right, Tejas?
Yeah, 9:30 is a late, like 8:30 or 9 is fine.
Yeah, I'm only thinking 8:30. It causes trouble to them for the dinner. Is 8:30 okay, Srinidhi?
yes, sir, I'll finish dinner before it, sir.
Okay, so you're saying you prefer to have a class of not today, right? You prefer to have the doubt session today. Okay.
No problem, sir. Like if you can't take the class on Tuesday and Thursday, so you can teach today, no problem. I'll try to cover them next week.
Okay, I will let you know. I will let you know in the next 20 minutes. But doubt session will definitely have it today. We can have it after the second class today, doubt session.
Yes, sir.
Okay. I'm definitely mostly not be able to teach on. I will mostly not be able to teach on Tuesday, and I don't know. See, it's not clear to me whether I'm taking more classes or I'm taking less classes. I think I'm pretty much on schedule. It looks like. I only wanted to teach one more class, but I understand. So I'll take a call within the next half an hour and let you know.
Sure, sir. Okay.
In any case, I will have the doubt session. I'll also send a link, message for the doubt session. Okay.
Okay, sir.
Yeah. Cool. Okay. Thank you.
Okay, thank you.
Yeah. Stop.